Alright, in this next video we're going to do another example using the method of undetermined coefficients to solve a non-homogeneous second order differential equation. Again, we call one non-homogeneous, and I'm using the notation NH to denote that, if you have a forcing function on the right hand side and all the other terms involving the unknown function y on say the left side. So our forcing function for this example is negative 3 e to the negative 2t. Alright, so we're going to go through the steps again, and the first step is to reduce this to the corresponding homogeneous equation. Alright, and then by substituting in y equals e to the st, look at the corresponding quadratic equation. In this case it would be s squared plus 4s plus 13 equals 0. Now this is a quadratic equation which we can't solve by factoring. We'd have to either use the completing the square technique or the quadratic formula. So let's use the quadratic formula. So we're going to get negative b, which in our case is 4, so negative 4 plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. Alright, a is 1, b we said was 4, c is 13. So we get negative 4 plus or minus the square root of 16 minus 13 times 4, which is 52, all divided by 2. Alright, now simplifying inside of the square root, we're going to get s is equal to negative 4 plus or minus, alright, 16 minus 52 is negative 36. Okay, so we can see we're going to get a complex root here. Alright, and then simplifying this down, we would get negative 4 plus or minus 6i all divided by 2. Alright, and then we don't forget to distribute this division up into each term, so we get negative 2 plus or minus 3i is our complex, our two complex solutions to that quadratic equation. Now, what we've learned from before is if we have a complex solution, all right, we only need the one with the positive imaginary part. All right, and via Euler's formula, this leads us to the general solution of the homogeneous problem being a linear combination of e to the negative 2t times cosine of 3t and e to the negative 2t sine of 3t. Okay, so again, the negative 2 is coming as our exponent with t, as the coefficient of t, and the exponent of e. The 3 from the imaginary part from the 3i there is going inside the cosine and the sine. Alright, so that's step 1. Alright, so again, you don't need to show any work for that kind of step. We don't have to go through and use Euler's formula. We've done that enough in solving linear systems. Just if you know you have a complex root, write down the general solution as linear combinations of e to the at cosine and sine of bt. Alright, so that's step number 1. Alright, we have our general solution of the homogeneous equation, which we're calling y sub h. Alright, now we've got to find some particular solution, find one particular solution of the non-homogeneous problem. Alright, we denote that by y sub p. Alright, and from our previous work, right, we know that we're going to guess the structure of y sub p based on the forcing function. Alright, now what we're saying here is if we're going to have a solution to this differential equation, its first derivative, its second derivative, and the original formula must be somehow added together. Alright, second derivative plus 4 times the first derivative plus 13 times that original formula to come up with an exponential, to come up with negative 3 times e to the negative 2t. Well, hopefully it makes pretty good sense then your answer must involve e to the negative 3t. Whoops, not 3t, negative 2t. The negative e to the negative 2t is not just going to come out of anywhere, but it might not just be that by itself, so we're going to leave some wiggle room in here and say, all right, it's got to be probably some constant, some constant coefficient that we're going to now determine by plugging that into the differential equation. Alright, so we know what y sub p is. Now we need to take two derivatives so we can substitute it in. The first derivative by the chain rule is going to be negative 2 times a. A is a constant, so that's a factor that's going to come along for the ride there, times e to the negative 2t. Taking a second derivative, we're going to bring down another factor of negative 2, so that'll be 4 times a times e to the negative 2t. And now we're going to substitute y sub p into the differential equation to then hopefully determine that coefficient a. Alright, so what I like to do is substitute in, or rewrite the differential equation by replacing y by y sub p. Again, we're plugging in, we're checking, is it possible that option we wrote down for y sub p for the particular solution will work. Oops, no a here. And now what we're going to do is just substitute in what we found for the second derivative, the first derivative, the original formula. And let's do that now. Alright, so what was the second derivative? That came out to 4a times e to the negative 2t. First derivative was negative 2a times e to the negative 2t. The original function was a times e to the negative 2t. And we're saying that that's got to equal negative 3 times e to the negative 2t. Well, combining like terms here, alright, this is really just after dropping the parentheses and doing some multiplication. 4a times e to the negative 2t minus 8a times e to the negative 2t plus 13a e to the negative 2t, and all of that has to equal negative 3 e to the negative 2t. Alright, now combining our like terms together, what are we finding out here? Alright, what do we got here? We have, as a total, what do we got here? Negative 4 plus 13. So we're going to have in total 9a e to the negative 2t, and that will equal negative 3 e to the negative 2t. Alright, now we can divide both sides by e to the negative 2t. That's a non-zero function of t, so we can cancel those out. So this tells us our equation is really 9a, 9a equals negative 3. Dividing both sides by a, we get negative 3 over 9, or negative 1/3. Okay, so what is y sub p then? Or y sub p of t? It's going to be negative 1/3 times e to the negative 2t. Alright, so that's most of the work for this example. Alright, and I've got other examples, post videos to those linked out to in Lumen as well. Alright, so what is our answer then? Alright, what's our general solution? You take your result from the first step, which is k1 e to the negative 2t, cosine of 3t plus k2, some arbitrary constant, which we could determine with an additional value problem, e to the negative 2t sine of 3t, and then plus y sub p, which we just figured out to be negative 1/3, so we can say just minus 1/3 e to the negative 2t. Alright, that would be a general solution. If that's all we were asked to find, then we would stop there. This problem has initial conditions associated to it. Y of 0 is 0, and y prime of 0 is 0. Again, I'm going to forego these steps, but we would need to take the derivative, which would in this case be a little bit tedious. We'd have to use the product rule here to differentiate the first two terms, and also the chain rule when we differentiate the e to the negative 2t and the cosine and sine of 3t. If you go through and do that, you can verify that k1 will come out to 1/3 and k2 will come out to be 0. Alright, so if we plug those things in, what would our actual answer be to the initial value problem? We would have 1/3 e to the negative 2t, cosine of 3t, k2 comes out to 0, so the second term would go away, and then minus 1/3 e to the negative 2t. Alright, it's clear that both those terms, hopefully it's clear to you, and I've got the graph below, are going to approach 0 as t gets larger and larger. Alright, so I've got the graph down below here. We do see some oscillation coming in there, alright, because of the cosine and sine factors, but the multiplying them by e to the negative 2t makes that damp out quite quickly. Alright, so that's another example using the method of undetermined coefficients.